Comparison instructions, but using masks. In the manual, we had you decrease the preset of your timer data type anytime to 4,000 thousandths of a second. And then we had you reset and then enable the timer on delay instruction and observe the greater than instructions, making note of the preset value when each output energizes. So we flip that on and you see 0, 1, 2, 3. And of course it's easy to answer the questions because when the accumulate is greater than 1,000, 2,000, 2750, and 3250, these outputs come on. And those were the answers: 1,000, 2,000, 2,750, and 3,250 milliseconds. And of course, this is just going to sit here until you reset the timer. And we don't have any reset for the timer in this code. How would you modify the logic to have them all on to start with and then de-energize as the comparison instructions go true and all remain de-energized until you toggle the enable input? Ponder this before you go to the next exercise and actually edit the logic. So if I turn off the run enable and back on, it executes again. They all start off and then they go on as the greater than instructions become true. We wanted you to edit the logic, figure out how to do it on your own. If not, then turn the page and you're going to convert all of these to less than instructions. Okay, we made those edits. Notice that they're all on because the anytime timer data type accumulate value is 0, which is less than 1,000, less than 2,000, less than 2,750, and less than 3,250. If I enable the timer, then they're going to go off and stay off until you reset the timer again. Enable the timer on instruction and observe the less than instructions, making note of the accumulate value when each output de-energizes. 1,000, 2,000, 2,750, and 3,250. How would you sum up a comparison between the greater than and the less than logic? Reverse order of the states would be a good, easy answer. Then I had you modify your logic once again. I then asked you to modify your logic. It pulses the outputs for 1/2 of a second, that's 500 milliseconds, each, instead of energizing and remaining off for the duration of the preset, as with the greater instructions, or all on and de-energizing with the duration of the preset, as with the less than or equal to instructions. Okay, let's reset the timer. And you see that they pulse on for 1/2 second each. Now the interval between the pulses is slightly different. That's because once you enable the timer, 1 second passes before you see the first 1/2 second pulse. Then a 1/2 second passes before you see the second 1/2 second pulse. And then you see a 1/4 of a second between the end of this pulse and the beginning of the next pulse. And then there is no interval between the end of this pulse and the beginning of this pulse. So let's watch that one more time. You're going to, from the time that you reset this, 1 second, a 1/2, then a 1/2, then a 1/2, then a 1/4, then a 1/2 and a 1/2 right together. Do that one more time. You see the pattern. So your answers would be on at 1,000, off at 1,500. On at 2,000, off at 2,500. On at 2,750, off at 3,250. On at 3,250, and off at 3,750. Now, I want you to notice something. Notice that if it's less than 3,250, this is still on. If it's greater than 3,250, then this one goes on. So there's really, at the most, 1,000ths of a second between this rung being true and this rung being true, but watch what appears to be a greater interval. You see, it looked like there was a little bit longer interval in there. That's because the relay doesn't de-energize instantaneously. So this one's still kind of on when this one is turning on. But anyway, this is the logic and those were the answers. Then we had you do the number line thing. I'm going to describe the answers. The first one, it gave you the result, and we had an open circle on 1000 and 1500 with the line interconnecting. The second one would be an open circle on 2000 and 2500 with a line connecting the two circles, meaning that it does not include 2000 and 2500, but it includes everything in between. Remember, an open circle is exclusive. A closed circle, the completely filled, is inclusive. Then the third one, that would be output 2, the third line. You have an open circle at 2750 and an open circle at 3250, which is between two of the tick marks on the line, and then you have an interconnecting line between those two open circles. Then the fourth one, which is input 3, or output 3, you have an open circle at 3250 and an open circuit at 3750 with a line interconnecting the two. Next we did the less than, and we had you delete all of your logic, delete all of your program tags, and start afresh. First question in the manual, is this rung of logic true? Let's geezer this up, at least for now, until we have more complex logic. The answer is no, because 0 is not less than 0. Now remember, these are values, they're members of a 30-dent array. So it's not that 0 is less than 1, that's the element of the array, not the value. The value for each is 0. Where would both values be on the number line? Well, a number line, picture in your mind, is a horizontal line in front of you. Right in the center of the line is a tick mark, a little vertical dash, and above it says 0. Everything to the left goes -1, -2, -3, -4 towards the more negative number. Everything to the right of 0 goes 1, 2, 3, 4, 5, more positive. So both of these values, value 0 and value 1, they're both 0. They would be right on the 0 tick mark. So it would be a solid circle right on the 0 mark because it is and includes 0 and nothing else. The rule is simple. Anything to the right is greater than anything to the left, and anything to the left is less than anything to the right on the number line. Change the value 0 to a -1. Is the rung true? Yes, it is, because -1 is less than 0. Reverse the values. Make this 0 and this -1. Is the rung true? No. Place both values on the number line. Now remember that this is not less than and everything less than. There's just two values here, 0 and -1. So when you put these on the number line, you'd have a solid circle on 0 and a solid circle on -1. The value furthest to the right is greater or less than the value to the left on the number line. The answer is greater than. To make the rung true by changing source A, what is the closest value to the current value that you can use to make this true? So if we're going to change to, right here, if we're going to change source A to make it less than -1, what is the closest number to -1 that is less than -1? That would be -2. And you see now the rung is true. Place these two numbers or two values on the number line. On the number line, to the left of 0, you would have a solid circle or a solid dot over -1 and a solid dot over -2 and no connecting line. It does not include anything between -1 and -2 because we're working with whole numbers here. It doesn't include fractions. Then I had you modify the logic. Now you see we have an OR expression. If this is true or this is true, then energize that bit in memory. And this instruction addresses local 10 data 0 by way of this pointer true_00. So if either one of these or are true, then this is going to be on. Is 0 less than 0? No. Is 0 equal to 0? Yes. So this is less than or equal to. And I know you've heard that expression before. Is this rung true? Yes. Are both instructions true? No. Which instructions are true? The equal is true. Which instructions are false? Less than is false. Change the value of value 1 to 2. You can change it any place you want that you see it. Is this rung true? Yes. Are both instructions true? No. Which instructions are true? The less than is now true. Which instructions are false? Equal. The equal is now false. So this is true and this is false. Remember that I explained to you that you cannot look at these instructions and see a visual indication whether they are true or false. You have to actually look at the values and evaluate them for yourself. Now we're going to show you a way to emphasize that next. Represent the combination of these instructions on the number line. Anything less than 2. How many values are there less than 2? Well, for whole numbers, 1, 0, -1, -2, -3, all the way down to -2 billion, whatever the limit is for a double integer. So on the number line, you would have a solid dot on 2, not -2, but +2, and then you would have a connecting line that goes all the way to the left with an arrow pointing to the left to indicate that it goes on all the way to the end of the lowest possible negative number for this data type. Just for grins, smiles, I had you create a dent tag called TrueBit and then add 2 OTE instructions using TrueBit bit 0 and TrueBit bit 1. That way you could easily see which of these instructions are true. If we change this to a 0, the rung is still true, but the same instruction isn't true. This might be something that you want to do as you're learning these comparison instructions, is to put a true bit after the instruction so you can see whether or not that instruction was true. Now, that doesn't always work out if you have these instructions in series. But the goal here was to make it obvious which instruction was true. And as I said in the manual, because the comparison instructions do not highlight when they have a true outrung state, you have to read the values and decide for yourself if they are true or not. By adding these true bits, it allows proof of the state. You would not do this in a practical application. We do it here strictly for clarification. Then I had you add another rung. I'll just add this. I won't pause. New rung, LEQ space OTE. So you see I'm using ASCII. In ASCII text, you have another choice there, but don't do that. Neutral text is going to require something different. Well, I messed it up because I clicked over this, so let me do that again. LEQ space OTE, enter. See, that puts in a less than or equal to and an OTE. We're going to use the same values, value 0, grab that, drag it down, value 1, and this is going to be true _01. Now that's not one of these true bits. We could have used those, but we didn't. This is just going to be a Boolean tag all by itself. Finalize all edits. And you see that this is now equal to this. So let's change this to -1. And now you see this is true and this one's not. But this remains true. These two instructions in a OR expression are equivalent to this one instruction. If you want less than or equal to, then use the less than or equal to instruction. Don't bother convoluting your code by using these two instructions. Go ahead and just try different values. Both of these are false, right? -1 is not less than -2, and -1 is not equal to -2. Therefore, they're both false, and that's false. Or I should say, this is off, and that's off. I ask you to just try some different values to see if you can find any instance where this is on and this is not. In other words, can you disprove that this code is not the equivalent to this code? Keep in mind these two OTEs are in there simply for clarification. They don't affect the functional logic. The less than instruction is exclusive of the value in source B. The value 2 is not less than 2, whereas 1 is less than 2. The function is therefore exclusive of the value of 2. So if we have 1 in here and 2, that instruction's true, but this instruction is exclusive of the value in source B. The less than or equal to is inclusive of source B because it's or equal to. That's what makes it inclusive, whereas these are exclusive. This instruction is inclusive. Here we have greater than or equal to. I had you try many different values for value 0 and value 1. Currently, 1 is not greater than 2 and 1 is not equal to 2. So neither one of these are true. This is not on and neither is this. If I put in a value where they're equal, both 2, then you can see that this instruction is now true, that bit is on. This instruction is true and that bit is on. If I pick a value where the greater than instruction is on, the equal is going to be false, but this wrong is still true, that bit is on, this wrong is still true, that bit is on. So I had you try all kinds of values for value 0 and value 1 to prove to yourself that this instruction, the single greater than or equal to, is equivalent to this greater than or equal to. The greater than instruction is exclusive of the value of source B. The value 2 is not greater than 2, whereas 3 is greater than 2. The function is therefore exclusive of the value 2. The greater than or equal to instruction is inclusive of the value in source B because it's or equal to. So it includes the value of source B. The value 2 is greater than or equal to 2. The function is therefore inclusive of value 2 or source B. You can combine individual functions, less than, greater than, equal, in your logic, or use the functions that in themselves have combined two simple functions into a compound function, which we just demonstrated, the less than or equal to and the greater than or equal to. Lest you go off on a tangent combining not equal with less than or greater than in parallel combinations, we will quickly do one just for your own edification. What we did is we converted the equal to a not equal instruction. Now you see they're both true. And the question in the manual was, what is the only instance where the rung is false? And that is when value 0 is equal to value 1, therefore, if they're equal, then this is false, and if they're equal, this is false. So this rung is going to be true with the exception of when these are equal. So why even bother with the greater? You see, so don't combine not equals with greater than, less than. If you added a less than instruction in parallel with the greater and not equal, would it change the results for the true or false state of the rung? No, it would not. Try it and test it if you like. We'll quickly double click to put it in the edit mode, add a branch level, make it a less, put in value 0, value 1, and just for grins, we'll put in an OTE, drag that down, double click, click backspace 2. So we have 3 unique bits that we're doing. Okay, remember the only condition where this is, ignore this down on the bottom. This is no longer in play. We're just looking at this mess. If I make these equal, then that's false. If I make it any other value, it's true. So whether this is less than or greater than, you see what I'm saying? If it's greater than or less than, it's going to be true. The only time it's going to be false is when they're equal. So I guess if you came up with some reason to exclude a value, I can think of a lot better ways to do it than this. But I just had you do this to keep you from going off, wasting your time combining greater than, less than with not equal. Okay, if you represented the combination of these instructions on the number line, the values for which the true bit 0 would be energized with either of the values held at 0 and the other varied from -10 to +10. On the number line, on 0, you would have an open circle, meaning it does not include 0. Keep in mind that we're making one of these 0. So it does not include 0, but it does include everything above 0 and below 0. The answer is really simple. With both values set to 0, you have nothing. That's why you have an open circle on 0. But any value, if we go -1, see, then it's true. If we go +1, it's true. The number line would be an open circle on 0 and a straight line to the left and right from 0 in both directions, meaning it includes everything else. Now we come to a really fun instruction, the mask equal. And in this case, I put the mask equal and the equal, I won't say side by side, but one above the other so you can compare the results. Well, 1 is not equal to 0, and yet the upper instruction is true, and the lower one is not. This will be your introduction to the concept of a binary mask. This is not the only instruction that uses a mask value. But once you've learned the nature of a mask value here, you can apply it in all the other instructions. This is a mask equal to instruction. A binary mask allows you to execute a function between 2 instances of the same data type. A 1 in the mask means the data bit is passed or compared, meaning these are dents, 32-bit dents. The mask is also a 32-bit dent. And a 32-bit dent is full of 1s and 0s. It can be all 0s, all 1s, or any combination thereof. Each of the 32 positions can contain a 0 or a 1. If the position contains a 1, then the result of masking the source or masking the compare will be the actual value. Let's move on here. A 1 in the mask means the data will be passed or compared. A 0 in the mask in that position means the data bit is blocked or not compared. Typically, the source, mask, and compare values are all the same data type. They should be. If you mix integer data types, the instruction fills the upper bits of the smaller integer data types with zeros so that they are the same size as the largest data type. Very important point to note. Now, it's not going to change the results because it's filling the upper bits with zeros. When you enter a mask, the programming software will default to decimal value. If you want to enter a mask using another format, precede the value with the correct prefix. And we show you examples in the manual for those prefixes. The question that you need to ask yourself is, why is rung 0 true and not rung number 1? They have the same values for value 0 and value 1. So the answer is value 0 through the mask is 0, and value 1 through the mask is 0, and 0 equals 0. So value 0 is 1, and value 1 is 0. They're not equal. But if you pass through a mask of all zeros, the result for value 0, even though it's 1, the result, the mask value result, will be 0. And of course, whatever the value in value 1 is, whatever it is, if you pass it through a mask value 0, it's not going to be compared. Just for grins, we'll change this to 1. True. Change it to 2. True. Change this to 5, 6, 7, 8, 9. True. As long as you're passing the value through a mask value of 0, the result of masking this value is 0. The result of masking this value is 0. And 0 equals 0. We'll put this back to something more reasonable. Let's look at these two illustrations right here. These were in your manual. Look at the upper one. You have a value of 7. For value 0, now I'm just using a 16-bit integer just to save space on the page. The fact that they're dense is irrelevant. We're using integers here. The concept is the same. So 7, binary, if you read from right to left, it's 1, 1, 1, and then all zeros. However, because the mask value is 0, the mask, past tense, source value comes out 0 because all of the values are blocked from falling into the mask source value. Value 1, which is 6, which reading in binary would be 1, 1, and then going to the left all zeros. However, if you pass it through the mask value of all zeros, then it's blocked. The mask compare value for source B is going to be 0. So you're comparing 0 to 0, even though the value 0 is 7 and value 1 is 6. Now, if you look down below, instead of a mask value of 0, we put in a mask value of 120. And in binary, from right to left, would be 0, 0, 0, 1, 1, 1, 1, and all zeros. The zeros here, they are passed through, but they're zeros anyway, so nothing changes. Same thing down here. So you still end up with a mask source value of 0. Here we change it to 122. And we did that on purpose so we could have one value from the actual source of A and B, source A and source B, value 0, value 1, pass through. Well, the source A, or we'll just say value 0 is 7 and value 1 is 6. Well, 7 is 1, 1, 1 and 6 is 1, 1. So the second position for both 6 and 7 is 1. If that's the only thing that you legitimately compare between the two, then the masked source value is going to be 2, and the masked compare value is going to be 2. So they would be equal. even though 7 and 6 aren't equal, the actual bits that you want to compare, they are equal. Now, working with mask values can be quite confusing. I did show you another rung in the lab. I didn't actually tell you to do it. I just gave you an example. I created that rung that has some exclusive, inclusive OR statements and OR statements for the different values, value 1 through value 6, comparing value 0, value 1 to come up with a true statement that would behave the same as this logic. The main point there was to show you that the mask equal instruction is much easier to use than writing this convoluted logic. The problem with mask values is understanding how they behave. So if you keep in mind that how that mask value is applied, it is put up against value 0. Wherever the mask value has a 1, then that value in value 1, that bit in value 1 is considered. If there's a 0 in the mask position, then it's not considered. And what you end up with is a mask result for the source and a mask result for the compare. And if those are equal, then the instruction is equal.